All right, welcome back to our video series on creating a maze solver in Java. In this video, we'll be doing a breadth-first algorithm to solve the maze. Unlike a depth-first search, there isn't a easy recursive version of breadth-first search. So we only have the iterative version, but the good news here is that the breadth-first search is extremely similar to depth-first search in implementation. In other words, instead of putting the neighbors of the current node at the front of a stack so that it's the first one that comes off. So we keep going in the same direction over and over till we hit a dead end. With the breadth first, we're going to put the neighbors at the end of a queue. Okay, which means that we're going to go in all directions as we go out, which is what you saw in the videos that you watched. So what that means is we can actually reuse a lot of our code from our depth first search. So let me show you how to do that. I guess the first thing is going to be, let's go ahead and update our maze tester. So instead of calling DFS, it's going to call BFS, and which means we now need to write a BFS method. So I'm going to grab my entire DFS method. The whole thing. I'm going to copy it. Control C, and again at the very top of this program I'm going to go ahead and paste it. Okay, now remember what I said, the biggest difference here is, well, that this is a B instead of a D, and that instead of, we're still going to remove off of the front, we're still taking off the front, but when we go to add things, we're going to add them at the end, which means we don't need to say add 0, we can just say left, up, right, down. Now the other difference is we actually want them, the order doesn't matter because we're actually going to go in all 4 directions every time. So I'm just going to save this for right now. And we'll go ahead and compile. Don't get any errors. And we'll go ahead and run it. Maze tester. You'll notice that we get something interesting happening, right? So we are seeing dots here, but what we're seeing is we're getting dots removed. And that's because here at the end of our depth first search, we had it backtracking to remove. And while we are going to do that it doesn't work quite the same way. What we're going to need to do is, well, first off, just to show that this actually is working, let's go ahead and get rid of this whole else block. So I'm going to delete this and save. Recompile. I think I missed a curly brace. Yeah, I think I deleted an extra curly brace. Recompile. And run. Maze tester. Okay, so we can see it is solving the maze. But as you would expect with a breadth first search, it's filling in a whole bunch of the maze. It's filling in all these parts that we aren't actually going to. In order to get the actual path for the maze, what we're going to need to do is when we get to the end and we break out of this while loop, we're going to use what's called a backtracking algorithm. We're going to check and see if we're actually at the end. And then if we are, we're going to build another array list that we're called a path. That's going to be the parents of each node from the end back to the beginning. Okay. And so what we'll do is, again, notice this is after the while loop. That's where I'm lining up here after the while loop. I'm going to say if current.isEnd, meaning we actually got to the end. So current is end. The only way that current knows that it's the end is if it's an F, which means we can't set visited to here anymore. Okay. What we're going to do is instead we're going to go ahead and move that down here. So if current is end, then current.setVisited. We're going to make an array list of nodes. I'll call this the path. And we'll say while current.getParent is not null. There's while it still has a parent, we're going to add current to the path. We'll then update current to be current's parent, so current.getParent. And so this loop is going to keep adding to our path. Okay. So then once we have all of these nodes, then we can traverse. Now what we want to do first, though, is we want to go through every node that we visited and mark it as unvisited, so that then we're going to go back through all of these nodes in our path and mark them as visited. So what we're going to do is we're going to say for node n in visited. All right, so each of these, so this is a for each loop, for each node n in visited, if the path doesn't contain that node. So if not path dot contains the node, then we'll say n dot clear visited. In other words, we'll go ahead and we're just going to go through every node that's in visited, right? If the path doesn't contain it, then clear it out. Okay, so we'll notice that we're getting this underlined current can't be resolved. That's because of the scope of the variable current. In our depth first search, we got away with putting this declaration of node current inside of our while loop because that's the only place current was used. But now that we need current outside of our while loop, we need to declare current outside here. So what I'm going to do is I'm just going to say node current equals start, right? And then in order to make sure that this current gets updated each time, I'm still going to leave this as current equals unvisit.remove. The idea here is it's possible that our start is our finish, I suppose. And so, I mean, still, this while loop should happen no matter what, but just to be safe. So, actually, not to be safe. Let me say that a different way. Not to be safe. If I say node current, right, then I still get a warning down here saying, well, it may not be initialized, right? So I don't want that. I'm just going to say node current equals start. And then that way I don't get that warning. And so now if we compile this, don't get any compile errors. And remember the thing we added was our path. So let's see if that actually worked. We're expecting a path. Okay. Now notice what we have going on here. It's nothing's happening. But it's not that nothing's happening. We have an infinite loop. Okay, so let's figure out why we have an infinite loop. So I think before we can add into our maze right here, I think we need to make sure that we haven't already been there. Right? So if left is not equal to null and left dot is empty and right, if up is not equal to null and up dot is empty, if right is not equal to null and right dot is empty, and finally down. All right, this makes sure that we're only adding empty nodes into our unvisited list, and that way we shouldn't get any loops. So let's just see if that accidentally fixes something. And we run. We can see that we now have a solution. Now it is leaving off that first node. Right, so current is no longer setting visited on the very first node, so we need to make sure that happens. And that's because our path, right, our path right here ends before we actually, so it stops. There's still one more, right, because current's parent is null, but current isn't. So what we need to do is say path.add current one more time. Compile and run. And now we can see we have start to end. Okay. So that's our breadth first search. Again, we were able to just reuse a whole lot of code from our depth first. A few things we had to add, but overall it was a lot. Because we've already done the depth first, it was shorter. So big takeaway, depth first search uses a stack breadth first search uses a queue, but otherwise the algorithm is essentially the same. It's just the order in which we visit the nodes. Because we're using a stack and depth first search, it goes all the way down until it hits a dead end. Whereas breadth first, since we're using a queue, it visits all of the directions, and then it visits all of the directions, and then all of the directions, and all of the directions. And so we get this breadth first. So thank you for watching, and we'll see you next time.